Okay, lecture 20, should know these definitions. Alright, I just wrote these out by hand. It made it a little bit easier. And label all the parts of the following reactions. Well, on this side, we have reactants. This side we have products. Sometimes you have one, you have to have at least one reactant, one product, but then it can go up from there. This here is the phase. So are these here, solid. So you have S, L, solid, liquid, gas, and aqueous. Those are the ones we deal with. This delta here means change, and when it's above an arrow it means heat. You've added heat. And then the arrow means yields. So, and then the numbers out front are the coefficients. So you have your reactants, your phases, their coefficients, that yields your products, and then if there's heat added you can put that above it. Here are some others. Reactants, products, phases. But here, when you see a metal like that, that generally means that it's catalyst. And then 150 degrees Celsius. This is the temperature at which the reaction was done. And because, well, isn't that heat? Yeah, it definitely is. You could put a delta sign there, or a delta symbol, but when you put a delta symbol, that could mean anything from a mild heating to hitting it with a acetylene blowtorch. If you want it to be at a very particular temperature, you can put that in. And then we have balancing equations. This is just a matter of getting used to the idea of balancing by inspection. What I normally do is I start with whatever's on the left and make sure that it's balanced on the other side. We can't lose any atoms. The law of conservation of mass says we can't, so we have one sodium over here. You have to take into account superscripts and coefficients. So we have sodium, sodium, 2 chlorines, 1 chlorine. Well, you might say, how about if we just put a chlorine here? Well, if you did that, you can't add new species without changing what the reaction is. You could certainly do this. This is a reaction that could occur, but it would be a very highly unstable one. So we can't normally add anything to either side. We have to just work with the coefficients. Since this is a 2, well, we could put a 2 here, but that changes the compound as well. We can only mess with the coefficients. So 2 chlorines. Now, by balancing the chlorines, we've put an imbalance with the sodium, so we put a 2 here. And you know that what's nice about these is that you know when you're right. When you go through and you find that you have the same number of each element on each side, you're done. If all you've done is messed with the coefficients, you just change the coefficients and you end up with same number on each side for each element, you are correct. The only thing that really can go wrong is, let's say we ended up with 4, 2, and 4 somehow. Well, you have to reduce it down. Say this is definitely balanced. If this was a 4, a 2, and a 4, that's balanced, but it's not the simplest form. We'd have to divide through by 2 to get it to this form. So be careful of that. That can occur. All right, we have these guys here. Phosphoric acid, and then phosphine is what this one's called here, or phosphorus trihydride, but it's called phosphine. Well, you want to mess around. You don't want to mess with the phosphorus because they're found in every single compound. And the more of these you do, the more you see that that's not what we want to deal with first. Oxygen is found in only one species on each side. So balance that first. Well, we have 3 and 4. Well, we can't multiply any number by 3 to give us 4. That's going to be a whole number. And using fractions is fine, but in this case it's easier to just say, since there's 3 here, 4 times 3, that's 12. Make this 3 times 4, 12. We haven't worried about the hydrogens at all. But now that we see that we've balanced the oxygens, what else has been balanced? Well, so I went with the oxygens because that was easiest. The hydrogens and the phosphorus are found in all the species, so I didn't want to mess with that. Oxygens are now balanced. We have 12 hydrogens, 12 hydrogens. 4 phosphorus, 3, 4, so it's balanced. So that will happen quite a bit. Once you balance one or more of the elements, sometimes the rest of them fall into line, and they should. This one I got away from me a little bit. Now, This one looks horrendous. It looks like, I'm going to actually rewrite it here. It looks like you have so much to do, but remember that, put a little room here, remember that these atoms, even though they are, looks like we have to balance each individual atom, I should say, we can balance parts of them, groups of them. Now look at the sulfate here, SO4. That doesn't change into anything. That sulfur remains part of the sulfate. So if we balance the sulfates, rather than balancing the sulfur and then the oxygen, well, that's a 3 here. We put a 3 here. And we've taken care of the sulfate. And that's okay to do. Even though there's an oxygen here, that oxygen did not come from the sulfate. It wasn't transferred in. So when you have a polyatomic ion that remains intact, use that to your advantage. And then we have, let's see, so we have ammonium here and ammonia. Well, every nitrogen here from the ammonia went and formed an ammonium. It added an H plus to it. So if we balance the ammonia and the ammonium as if they were the same thing, it's okay because we're just looking at the nitrogen. Forget about the hydrogen. We'll balance those later. But if you have NH3 and H4, there's 6 here, 6 ammonium, so we must have started with 6 ammonia. Now, if we look at the water, make sure I got, before we do the water, what else needs to be balanced? We have iron here. There's 2 irons, 1 iron, so that's an easy one. That's the only place iron is found in each of these. And then we have OH minus 3, so there's 6 of them total. Well, each of those OH minuses must have come from a water. You can see what happened. Each water gave an H plus to an ammonia to create the ammonium, and there's OH minus left over. Since there's 6 of these, that must be 6. So instead of dealing with each individual element, which would probably have taken all day, you can deal with parts of them. And I know that I jumped around, but it is a very complex reaction. It's pretty much the toughest one that you're going to see. So take a look at this and go through it and maybe come back to this lecture a few times until you see how and this is, let me double check, make sure. Yeah, so everything's balanced, and I did it by dealing with pieces of them rather than individual elements. Now this one, we have propane plus oxygen goes to carbon dioxide and water. We have 3 carbon, so put a 3 here. We have 8 hydrogen, so a 4 goes here. And then we have 3 times 2, that's 6 plus 4, 10. So we have 10 oxygens we need to balance, so we put a 5 here. And that's not actually what I wanted to do. Let's, I'm running out of time on the my videotape, so we'll see what it can do here. So this is 10. Let's try this one because it's a little trickier. Nothing wrong with that first one, but now we have carbon. There's 4, so a 4 here. We have 10 hydrogens, so a 5 would go here for the hydrogens. Now we have 8 oxygens, and then plus 5. So a total of 13 oxygens on this side. Now we have a problem because our oxygens aren't, if there was just one oxygen, we just put a 13 there, we're all set. But the oxygens come in pairs. So there's no number we can no integer we can multiply by 2 that will give us 13. That's okay, since it's just, this happens so much with these diatomic molecules, let's use a fraction. We wouldn't want to use it on a more complex system, but here, if we use a fraction, then we're balanced. 13 halves times 2, that gives us 13. That's what we were after. Well, even though it's balanced, and you'll see it like this sometimes if you stay on in the sciences, they'll leave it in this form for one reason or another. We need to simplify. And since we were balanced here, if you check it out, we'll find that everything's balanced. If we multiply through by the same number, it should remain balanced. Well, if we multiply through by 2, then this becomes 8, this becomes 10, and voila, we're balanced. So this is one of those times when using fractions would be helpful. Up here we could have done this with fractions, and you can try it if you want. It's not quite as easy. The only one I recommend using fractions for is when you're dealing with some number of halves, in this case 13 halves. And that is the deal.